There is a drawer somewhere in this description of reality that holds something, but only if you decide to look. Before that moment, the drawer is neither full nor empty. This chapter begins not with particles, but with the habit of assuming that things wait for us in fixed states. The question isn't what's inside. The question is whether inside means anything at all before the moment of looking. Something in physics decided to take this seriously. Wherever you are right now, the room around you has probably settled into its nighttime version of itself. Softer somehow. The edges less insistent. If there is a lamp on, it throws light in one direction and leaves the rest to get on without it. Maybe there is a window, and beyond it, the kind of dark that doesn't ask anything of you. This is a good place to begin. Not because the physics we're about to sit with requires darkness, but because darkness is one of the few conditions that actually invites you to stop assuming you know what's there. You probably walked past several objects today without looking directly at them. A bag by the door, a chair you didn't use, something left on a counter from the morning. And here is the thing that you assumed they were there. You didn't need to look. The bag was where you left it, the chair was where it always is, and whatever was on the counter had been sitting in its fixed position since breakfast, waiting, as objects do. With perfect patience and no ambiguity whatsoever. That assumption is so natural it doesn't feel like an assumption. It feels like the ground. Quantum mechanics arrived and quietly, almost without raising its voice, suggested that the ground is thinner than we thought. Not beneath your feet, not at the scale of chairs and bags and counters, but beneath that, at the level where matter stops being the version of itself you can touch. Something is happening that doesn't follow the same rules. The rules down there are different in a way that isn't a matter of our instruments being too crude, or our measurements being too rough. The difference is structural. It is not that we fail to know where a particle is. It is that the particle, in a precise and defensible and experimentally verified sense, does not have a location in the way the chair has a location. Not until something interacts with it. Not until the world in some form asks. This is where the drawer comes in. Imagine a drawer, closed. You are across the room from it and you have not opened it for a long time. Inside the drawer, you're fairly certain, there is a small object, a coin, let's say, though the coin is just a stand-in for something harder to picture. Now, in the ordinary world, the coin is in there. It has always been in there. It is sitting quietly in the dark with its head side up or its tail side up, one or the other, and the fact that you haven't looked doesn't change which. The coin has a definite state. It is waiting for, fully formed with its answer already chosen. Quantum mechanics walked up to that drawer and said, no, not rudely, not with any particular aggression. It just looked at the evidence very carefully and said, before you open it, there is no fact about which side the coin is showing. This is not a statement about your ignorance. It is a statement about the coin. This took a long time to accept, longer than it probably should have. Because the idea that an object exists in a definite state, whether or not anyone is watching, is so deeply woven into the way we move through the world that questioning it feels less like a scientific revision and more like being told that language itself was slightly off. We built everything on the assumption that things are a certain way, and that looking just reveals what was already true. The act of observation in ordinary life is passive. It doesn't change the answer. It just tells you what the answer was. But for a quantum particle, observation is not passive. Observation is participatory. When a physicist measures the spin of an electron, whether it is oriented in one direction or another, the measurement is not discovering a pre-existing fact. It is, in a very real sense, completing one. Before the measurement, the electron carries both possibilities simultaneously, not as a hidden coin with a concealed side, but as a genuine superposition, a condition in which both orientations are physically present in the mathematics that describes the particle's reality. And the mathematics works. It predicts what happens with extraordinary accuracy. The strangeness isn't a bug in the theory, it's a feature of the universe. You might be wondering somewhere in that place where thoughts and almost sleep begin to blur, whether this means anything for the world you can see and touch. Whether the chair is also, in some technical sense, uncertain. And the honest answer is that it's made of particles that were once exactly this uncertain, and that the solidity you trust is the result of enormous numbers of those particles interacting with one another, and with everything around them so constantly and so rapidly that the quantum ambiguity averages out into something stable. The chair is there. The certainty you feel about it is real. It is just built from a different kind of substrate than the certainty suggests. That is the consequence. Not chaos, not instability, just the quiet knowledge that something very old in our understanding was not quite right, and that the correction once made opened a door we hadn't known was there. And this is where I find myself arriving at something I wasn't expecting when I started thinking through this. The realization coming slowly, forming as I speak rather than before it, that the draw was never really about a draw. It was always about what we decided to call reality before we had enough evidence to know what reality was doing. We called it fixed because fixed was useful. Fixed let us build things, predict things, navigate through Tuesday morning without existential vertigo. And fixed was right. At the scale we needed it to be right. But below that scale, in the quiet places where individual particles do their work, the world kept its own counsel. It did not inform us that it was undecided. It just kept producing results that eventually forced us to consider the possibility. The drawer is closed again now. Somewhere in the dark behind it, something is held in suspension. Not hiding, not waiting, not one thing or another, but genuinely open in a way that only resolves when it meets the world. You don't need to open it tonight. There is a coin that carries both sides of itself through time, and what it means for something to be real before it becomes one particular thing is a question that physics answered and then kept asking in deeper registers for decades afterward. Which is something we will find ourselves moving toward without quite deciding to, as this night continues. If this kind of space is something you find yourself returning to, you're welcome to visit the channel page. There's more there, waiting quietly. There is a stone on a path and you can point to it. You can walk up to it and crouch down and place a finger against its surface and feel exactly where it ends and the air around it begins. It is there, specifically, in the way that only solid things at human scale manage to be. Quantum objects refused this arrangement almost from the beginning of the 20th century, and the refusal turned out not to be a mystery waiting to be solved, but something closer to the answer itself, a description of how certain things genuinely exist before the world closes in around them and presses them into a single nameable state. This chapter stays with suspension, not the dramatic kind, not the held breath before something breaks, the quieter kind, the kind that has no tension in it, the kind that exists the way deep water exists beneath the surface of a lake you are looking at from a long distance, present and real, and doing nothing that requires your attention or your understanding in order to continue being true. Think for a moment about what it feels like to be almost asleep but not quite there. The body has already let go of most of its obligations, the weight of it has settled. Breathing has slowed into something closer to tide than breath, moving in and out without instruction, without effort, without the sense that anyone is choosing it. And the mind is somewhere between its daytime architecture and the place it goes when it finally stops organizing itself for the night. Neither state, not quite. Something held between two conditions that both feel real and neither of which has fully claimed you yet. This is not a metaphor for quantum superposition, Or perhaps it is a little, but not in the way that is meant to make the physics feel friendlier. It is more that the sensation of existing between states is not entirely foreign to the body, even if the body almost never stays there for long, even if it always resolves into one thing or the other by morning. The electron does not resolve by morning. The electron in the right conditions holds its between state with a kind of structural commitment that has no equivalent in ordinary life, no furniture in the language of objects that sit on paths and wait to be pointed at. What physicists discovered, slowly and with a great deal of resistance from their own intuitions, is that a quantum particle in superposition is not simply undecided in the way that a coin spinning in the air is undecided, showing heads and tails in rapid alternation until gravity and a surface between them settle the matter. The spinning coin is always one thing or the other at any given instant. The ambiguity is in the time and the speed and the practical difficulty of measuring something moving that fast. The ambiguity is ours, not the coin's. But the particle in superposition carries something genuinely different. A condition in which two possible outcomes are not alternating, not hidden from view by their speed, but structurally present simultaneously, woven together in the mathematics that describes what the particle actually is at that moment, not what we happen to know about it. The distinction matters. It seems like a small thing, a question of whether the ignorance lives in the system or in the observer, but it turns out to be one of the deeper faults running through the bedrock of physics, the line between classical certainty and quantum reality, and everything on either side of it behaves according to different rules. A particle with spin, and spin is a property that has no real equivalent in the world of stones on paths, a kind of intrinsic angular momentum that doesn't require the particle to be rotating in any classical sense, can exist in a superposition of spin up and spin down simultaneously. Not one, not the other. Both in the only sense that the mathematics offers, which is the only sense the universe has confirmed through experiment, which is, in the end, the only sense that counts. When a measurement is made, when some physical interaction forces the question, the superposition collapses and the particle declares itself, becomes one thing, carries one value forward into the world. But before that moment, the particle was genuinely not one thing, it was held. There is a hesitation here, and perhaps it is worth acknowledging it rather than moving past it, because saying that the particle was genuinely not one thing before measurement risks sounding like a statement about human knowledge rather than about physical reality. And the difference between those two statements is the entire argument. Physicists have tested this. The tests are not theoretical. The Bell inequality experiments, conducted first in the early 1970s by John Clauser and later more rigorously by Alain Aspect and others, showed with statistical certainty that the correlations between entangled particles cannot be explained by any hidden pre-existing values, that there is no concealed coin waiting to be revealed, that the superposition was real in a sense that the word real was not quite ready to carry when the results came in. The physics settled the question, the intuition is still catching up. What remains, when the experiments are set aside and the mathematics is folded away for the night, is the image of something genuinely between, not undiscovered, not unknown, not waiting in a fixed state for a curious mind to come along and find it, but suspended in a condition that is its own kind of presence. The particle does not experience its superposition the way you might experience uncertainty. It does not wait. It does not choose. It exists in its distributed state the way a wave exists across water, spread and moving and real at every point along its surface, until something interrupts it and the energy finds a place to land. And then it is one thing and the between is gone, not lost, not destroyed, simply no longer the relevant description. the way the between of almost asleep becomes irrelevant the moment sleep arrives and takes over completely. It seems, though this is the kind of claim that needs to be held lightly, that softens the more carefully you look at it, that the universe genuinely tolerates this kind of openness at small scales, that it does not require everything to be decided before it is observed, that there is room built into the structure of physical law for something to be neither nor until the moment it becomes one. This is not a flaw. It is not an oversight in the design. It is, as far as the evidence goes, the way things actually are below the threshold where the quantum world hands off to the one we can walk through and touch and point at. The stone on the path is still there, specific, located, patient in the way that large, solid, thoroughly classical objects are patient, without drama, without ambiguity, without any need to be measured in order to maintain their particular position on the surface of the earth. But it is made of things that were never so settled. The atoms in it, the electrons around those atoms, the quarks inside the protons in the nuclei of those atoms, all of them carry a history of superposition, of having once been held between, of having resolved into particular states through the accumulated pressure of interaction after interaction across the deep time of the universe's unfolding. The betweenness did not disappear. It just compounded into something too vast and too entangled with everything around it to remain open, which is its own kind of story and one that belongs a little further into the night than this. For now there is just the image of something suspended, real, neither arrived nor absent, held in a condition that the mathematics describes with perfect confidence and the language describes with an imperfect grasp, reaching for something that isn't quite shaped like any of the words we already have. The suspension will not last. It never does. Something always interacts, always closes the gap, always brings the open thing down into one particular answer. But there is a duration before that, brief, unmeasured, belonging to no one, in which the particle simply is what it is, which is both, which is the between, which is the state that physics had to invent new language to describe because none of the old language was wide enough to hold it. What it costs to know which state it chose is something the next part of this will find its way toward, quietly and without rushing to arrive. For most of human history, probability was an admission. It was the number you reached for when you didn't know enough, when the actual answer was hidden from you by distance or complexity, or the simple fact that you hadn't looked yet. You said 50% because you lacked the information to say something more precise. The probability lived in you, not in the thing. Quantum mechanics changed that address. Consider a coin before it is flipped, not mid-air, before, sitting flat on a table, head side up, motionless, fully committed to one orientation. There is no probability in the coin at that moment. The probability is entirely in your ignorance of which side will face up after it lands. The coin, throughout its entire journey from table to air to table again, is always doing exactly what the laws of classical physics say it should do, given its starting position, its angular momentum, the air resistance, the surface it falls on. If you knew all of those values precisely, you could predict the outcome with certainty. The probability is a placeholder for missing data, nothing more. This was how probability worked in science for a long time, as a practical tool, useful, honest about its own limitations. Then something happened. In the early decades of the 20th century, physicists began accumulating results that didn't fit, not slightly off, structurally incompatible with the idea that probability was merely a confession of ignorance, the radioactive atom that decays at some unpredictable moment, the photon that passes through a polarizing filter or doesn't, with odds that can be calculated but outcomes that cannot be predetermined. the electron measured to have spin up when nothing in its prior history dictated spin up over spin down. These were not cases of missing data. They were cases where the data, all of it, had been collected, and randomness remained. The randomness was not in the observer. It was in the system. This is a hard sentence to let settle. It was hard for the physicists writing it down too. Albert Einstein, who contributed enormously to the early development of quantum theory, spent decades resisting this conclusion. His resistance was not ignorance. It was philosophical coherence. He believed genuinely and with careful reasoning that a complete theory of nature should not contain irreducible randomness at its foundations, that if something appeared random, it was because a deeper layer of description was missing. Hidden variables, the argument went, undiscovered quantities that, if known, would restore determinism to the picture. It was a reasonable position it lost. The experiments that eventually settled it came later. John Bell, a physicist working at CERN in the 1960s, derived a mathematical inequality, a boundary, that any hidden variable theory would have to respect in order to preserve a reasonable picture of locality and realism. The experiments that tested this boundary, refined over decades, found that the boundary was violated, not by a little. Consistently, clearly across many different experimental setups. The correlations between entangled particles exceeded what any pre-existing hidden variable could produce. The randomness was not a gap in knowledge. It was a feature of the system's actual state before measurement, which means probability in quantum mechanics is not the same thing it was before quantum mechanics. The word looks the same, the mathematics is familiar, but it is pointing at something different now, not at human ignorance, at genuine physical openness. An electron in a superposition of spin states doesn't have a hidden spin value that the measurement merely reveals. It has a probability amplitude, a complex number whose squared magnitude gives the likelihood of each outcome, and the amplitude is the most complete description available, not because we lack better tools, but because there is nothing more to describe. The probability is the physics. It is not a symptom of incomplete knowledge. It is the thing itself. This took time to absorb, decades really, and I want to be careful here, or rather more careful than I was a moment ago, because saying the probability is the thing itself risks making it sound more resolved than it is. The interpretation of what quantum probability means at the deepest level is still genuinely contested among physicists who understand the mathematics perfectly well. They agree on the predictions. They do not agree on what the predictions are telling us about the nature of reality underneath. The probability works, what it means for something to be probable rather than determined, what that implies about the structure of time and causation and the relationship between the world and the minds that measure it. These questions remain open in ways that are not merely philosophical but touch something unresolved at the center of the theory. So the idea is tested, held up, examined from different angles, and then allowed to remain uncertain. Not because the science is weak, but because the science is honest. What changed concretely is this. Before quantum mechanics, you could in principle draw a line between what you knew and what the world was doing, and the probability lived in the gap between those two things. After quantum mechanics, that line became harder to draw. In some interpretations, it disappeared entirely. The probability was no longer a bridge between your ignorance and a fixed fact waiting somewhere in the world. It became descriptive of a state that had no fixed fact beneath it, a state that was genuinely multiple until it became one. The numbers themselves didn't change much. You still write down a wave function. You still square its amplitude to get a probability. You still run the experiment and get a result that matches the prediction. The formalism is consistent and it works with extraordinary precision. What changed was what you were allowed to say the numbers referred to. What changed was the ontology, the question of what kind of thing a probability is a description of. And that is not a small change. That is a renovation at the foundation level carried out quietly. While the building above it continued to stand and the people inside it continued to move through their days without noticing that the ground beneath them had been understood differently. There are other places in science where probability appears: weather systems, evolutionary paths, the behavior of large populations. In all of those cases, the probability is epistemic. It reflects the limits of what we can track and compute rather than any irreducible randomness in the phenomenon itself. The weather is deterministic in principle. The evolution of a population is shaped by contingency that is, in principle, traceable back through a long chain of physical causes. The randomness in these systems is the old kind, the kind that lives in us. Quantum randomness is different in kind, not just in degree. It does not reduce, even in principle, to a longer chain of classical causes. It is not hiding anything. It is not waiting for better instruments. It is the thing the instruments find when they're as good as they can possibly be. Which brings us back almost exactly to where we began. Probability as admission, probability as honest acknowledgement that something is not yet known, that framing was useful and not wrong at the scales where it was applied, but it was not universal. Below a certain threshold of scale, the word continued to function, continued to produce correct predictions, continued to be written into equations that describe the world accurately, while meaning something that the people who first used it would not have recognized. The confession became a fact, the ignorance became an ontology. The coin on the table before the flip is still the same coin it always was. Head side up, motionless, committed. The probability there is still yours. But somewhere below the level of the table, in the atoms of the metal, in the electrons surrounding the nuclei, in the quantum fields threading through everything, the probability belongs to the world. And that small difference in ownership turns out to be one of the stranger things physics ever had to learn to say. He was not being whimsical. That is the first thing worth sitting with, before anything else about the cat or the box or the physicist who put them together in a thought experiment that was never supposed to become an emblem of wonder. Erwin Schrödinger was frustrated. The equation that carries his name, the one that describes how quantum states evolve through time, smooth and deterministic and precise, was producing conclusions that he found, in plain terms, unacceptable. Not mathematically, physically. The mathematics was fine. The mathematics was his. What the mathematics seemed to be saying about reality was what troubled him. And the cat was the complaint made visible. Frustration, dressed up as a thought experiment, handed to history, which kept the image and softened the argument. There is a particular quality to the air in a room where something is being disputed, not argued loudly, disputed quietly. The kind of disagreement that doesn't raise its voice because it knows the stakes are too high for noise. Schrödinger was in that kind of room, intellectually speaking, in 1935. The Copenhagen interpretation of quantum mechanics, the dominant framework of the time, associated with Niels Bohr and Werner Heisenberg among others, held that quantum systems exist in superposition until measured, and that the wavefunction, that smooth mathematical description of all possible states, collapses upon observation into a single definite outcome. The framework worked. It predicted experimental results with precision that nothing else could match. Schrödinger thought it was saying something absurd. Not wrong exactly. Absurd. There is a difference, and the difference matters here. The thought experiment goes like this. A cat is placed inside a sealed box. Also inside the box, a small amount of radioactive material, a detector, and a device connected to a vial of poison. If the radioactive atom decays, an event governed entirely by quantum probability, with no classical cause determining when or whether it happens, the detector triggers the device, the vial breaks, the cat dies. If the atom does not decay, the cat lives. The box is sealed. No observation is made. An hour passes. According to the logic of the Copenhagen interpretation, the radioactive atom, unobserved, exists in a superposition of decayed and not decayed. Both states are present in the wavefunction. Both possibilities are physically real in the only sense the theory provides. And if the atom is in superposition, then the detector is in superposition, and the device is in superposition, and the poison is in superposition, and, here is where Schrödinger planted his flag, the cat is in superposition, alive and dead simultaneously, until the box is opened, until someone looks. This, he argued, was ridiculous. Not because cats are special, because the logic that produces a cat in superposition is the same logic being applied to electrons and photons and atoms, and if that logic breaks down visibly at the scale of cats, if it produces conclusions that violate every ordinary understanding of what it means for a large object to exist, then perhaps the logic itself needed examination. He was right that something needed examination. He was not right, I think, that the examination would lead where he expected. That is a personal reading, and it may be worth marking it as such. But the decades of physics that followed his thought experiment did not resolve in his favour. They resolved in a direction he didn't anticipate, and the cat survived conceptually as both a warning and a window, just not the one he built it to be. The air around the Copenhagen interpretation in 1935 was complicated. Bohr and Einstein had been in disagreement for years. Einstein, like Schrödinger, believed that a complete theory of nature should not require the act of observation to bring reality into being. Observation, in their view, should be passive, a reading of what was already there. Bohr's position was harder to characterize and remain so. He did not, as is sometimes claimed, assert that nothing exists before measurement. He was more careful than that, more oblique. He insisted that the quantum formalism was a complete description of what could be known about a system, and that asking what the system was doing in the absence of measurement was asking a question that the theory, correctly understood, was not obligated to answer. This is not the same as saying the cat is both alive and dead. It is something more careful, more difficult to hold. But the image of the cat persisted. It persisted because the image was vivid, and the underlying argument was subtle, and history tends to carry the vivid thing further than the subtle one. The cat became a symbol of quantum strangeness when it was designed to be a reductio ad absurdum, a proof by showing that the conclusion is impossible. The joke, if there is one, is that the conclusion turned out to be more defensible than the complaint. There is a version of this story I almost reach for here. Something about the way complaints sometimes accidentally map the territory they were trying to dismiss, but it collapses under its own weight before it arrives, and perhaps that is appropriate. The thought experiment does enough on its own without the addition of a frame around it. What Schrödinger gave physics unintentionally was a precise articulation of where quantum mechanics becomes strange at scale. The transition from quantum behavior to classical behavior, from the world of superpositions to the world of cats that are unambiguously alive or dead, is not explained by the basic formalism of quantum mechanics. The formalism describes the evolution of quantum states. It does not describe from the inside why large systems made of quantum parts seem to behave classically. This gap is real. It is not a secret. Physicists have worked on it for decades, and the answer that has emerged, decoherence, the process by which a quantum system loses its superposition through interaction with its environment, is a genuine answer, partial and ongoing that Schrödinger did not have access to in 1935. Decoherence will find its own place in this later. For now, it is enough to note that the gap he pointed to was real, even if his proposed resolution, that the theory must be wrong, was not where the evidence eventually pointed. The box is still closed in some sense, not literally. The thought experiment has no physical instantiation. No cat was ever placed in a quantum mechanical predicament of this kind, and the practical reasons for that are as much about physics as about ethics. Quantum superposition at the scale of living things is not something that can be maintained. The environment intrudes immediately. Interaction happens. The open state collapses before any device could hope to measure it. The cat, in reality, is always one thing before you open the box. The quantum event that might trigger the poison has, by the time you consider opening the box, already interacted with enough of the world to have a definite outcome even without your observation. But in the space of the argument, in the clean logical air of 1935, the cat was suspended. Both. Neither. Waiting for a look that would, according to the framework being contested, bring one reality into being at the expense of the other. Schrödinger wanted that to sound absurd. For a long time it did. It still does, in a way, at the scale of cats and rooms and boxes and people opening lids to find out what happened. But at the scale where the physics actually lives, at the level of the atom that may or may not have decayed, the absurdity has a different texture. It starts to feel less like a reductio and more like a description. He died in 1961, having seen decades of experimental confirmation of the theory he was challenging, having seen the interpretational debates deepen rather than resolve, having seen his cat become one of the most recognizable images in popular science, not as a critique, but as an invitation. What he intended and what he produced are not the same thing. This happens sometimes in physics. The argument goes one way and the implications go another. And the image that was meant to close a door ends up being the thing people walk through for the next century, looking for the room on the other side. The door is still there, slightly open. The light from the other side is not strong enough to see by. But it is enough to know that something is in there, unresolved, waiting not to be discovered, but to be understood in a way that the language of boxes and cats and observations was never quite built for. Which is perhaps where the frustration began, and perhaps where it quietly continues. Time moves through this chapter before the chapter moves through time. Something happens before the central idea arrives. A kind of duration that belongs to the approach rather than the destination. Superposition has a lifespan, not a fixed one, a contingent one, shaped by what surrounds it, what touches it, what the system is made of and how isolated it manages to remain. This chapter stays with that duration, with the question of how long openness lasts before the world presses it closed. A quantum system does not announce when it begins. There is no starting gun. An electron is prepared in a superposition state, spin up and spin down simultaneously, in the only sense the physics provides. And then it exists in that state, evolving. The wave function carrying both possibilities forward through time with complete mathematical regularity. The Schrödinger equation governs this evolution. It is deterministic. It is continuous. It produces no collapse on its own, no resolution, no moment at which one possibility wins and the other concedes. The equation simply moves the state forward, and the state remains open. This is the part that takes a moment to register. The openness is not fragile in the way that fragile things usually are. It does not tremble. It does not strain under its own ambiguity. It simply continues, the wave function evolving according to precise mathematical law, carrying its distributed reality through time without any internal pressure toward resolution. left entirely alone, shielded from every external influence, interacting with nothing, touched by no field or particle or fluctuation of any kind, the superposition persists, indefinitely in principle. The clock runs and the state holds, and nothing in the physics demands that it choose. But nothing in the universe stays entirely alone. This is where duration becomes concrete rather than abstract. How long a superposition lasts depends almost entirely on what the system is and what surrounds it. For a single electron in a carefully controlled laboratory environment, shielded from electromagnetic noise and thermal fluctuation, the coherence time, the duration over which the superposition remains intact, can stretch into microseconds, milliseconds, in some experimental setups seconds or longer. These are extraordinary durations at the quantum scale, achieved through extraordinary effort. Dilution refrigerators cooled to temperatures a fraction of a degree above absolute zero. Electromagnetic shielding that reduces external fields to near nothing. Vacuum chambers that remove almost every particle that might collide with the system and carry away information about its state. All of that technology, all of that effort, to preserve a few milliseconds of openness. For a larger system, a molecule, say, or a small cluster of atoms, coherence times shorten dramatically. The environment grows more present, more insistent. More particles nearby means more potential interactions, more channels through which information about the system's state can leak outward into the world. Each interaction is a kind of question, and each question nudges the system toward an answer. The superposition does not collapse violently. It erodes. Gradually, then completely, the way a sound fades in a room with soft walls, not cut off but absorbed. Physicists call this process decoherence. The name is precise. Coherence in quantum mechanics refers to the definite phase relationship between the components of a superposition, the property that makes interference possible, that keeps both possibilities genuinely present in the physics rather than merely statistically mixed. When coherence is lost, the superposition does not exactly collapse in the dramatic sense that the Copenhagen interpretation sometimes implies. It becomes entangled with the environment. The possible states of the system become correlated with possible states of the surrounding world, and the result is something that looks, from the outside, exactly like a classical probability distribution. The quantum openness hasn't been destroyed. It has spread, diluted into the environment until it is, for all practical purposes, unrecoverable. This is the implicit process at work throughout the chapter, not announced, but present. Something moving through steps that do not declare themselves as steps. For a dust particle floating in air, the coherence time is estimated to be something on the order of 10 to the power of negative 31 seconds. A number so small it has no sensory equivalent, no scale in ordinary experience, nothing to attach it to except the recognition that it's essentially zero. The particle is classical before any measurement is made, before any conscious observer is involved, before the word observation becomes relevant in any meaningful sense. The air around it, the photons of ambient light bouncing off it, the thermal vibrations moving through it, all of these constitute a continuous measurement, a constant stream of interactions that drain the quantum openness away before it can accumulate into anything detectable. The thickness of a moment, then, is not fixed. It depends on what the moment contains. Here is where something shifts in the texture of the chapter, not a conclusion, more like a change in light, an isolated atom in deep space, far from stellar radiation, far from other matter, drifting into the cold between galaxies, carries its quantum state in a silence that has no laboratory equivalent. No shielding is engineered. The silence is simply there, the natural condition of that distance. And in that silence, the atom's superposition, if it was prepared in one, persists, not because anything is protecting it, because nothing is disturbing it. The coherence time stretches not into milliseconds, but into something approaching the timescales of cosmology. The atom drifts, the wavefunction evolves. The state holds its openness the way a still pond holds its surface, not because it is strong, but because nothing has moved through it. This seems, to whatever extent a considered view is worth offering here, like one of the stranger implications of quantum mechanics. That isolation is not emptiness, but preservation. That the deepest silences in the universe are also, in some technical sense, the places where quantum openness lasts longest, where the thickness of the moment stretches into durations that no human instrument will ever measure, because no human instrument could survive the distance required to reach them. The superposition out there is real, unobserved, uncollapsed, existing in a state that the physics describes with confidence and the imagination reaches for, and almost, though perhaps this is where confidence should grow more careful, where the claim should be held a little more loosely than it was a moment ago, perhaps can picture, if picture is even the right word for something that has no surface and no colour and no position in any ordinary sense. Back at human scale, the thickness collapses to almost nothing. The richness of interaction that makes the everyday world stable and navigable, the constant exchange of photons, the thermal jostling of molecules, the dense web of electromagnetic fields threading through ordinary matter, all of it conspires to make classical reality feel inevitable. And it is, at this scale. The decoherence is so fast and so complete that the quantum substrate beneath the visible world is effectively unreachable without extraordinary intervention. But the substrate is there. The process that produces classical reality out of quantum possibility is ongoing, constant, universal. Every object in the visible world is the output of a decoherence process that is still running. The stone on the path, the lamp in the corner, the ceiling above wherever this is being heard, all of them are classical because they are embedded in environments so rich with interaction that their quantum coherence lasted less than any interval of time that has a name. The thickness of the moment for them was immeasurably thin. For the electron in the dilution refrigerator, carefully shielded, it lasted long enough to be measured, to be used, to carry the quantum information that makes certain technologies possible and others conceivable. For the atom in the intergalactic dark, it has been lasting, uninterrupted, since whatever event last touched it, which may have been longer ago than the history of this planet. Duration in quantum mechanics is not a fixed property of superposition. It is a relationship between the system and everything that is not the system, between the openness inside and the pressure outside. And the question of what happens when that pressure finally arrives, when the environment closes in and the state must become one thing, is the question that the next part of this will find itself moving through without hurrying toward it. Right now, at this moment, in the regions of space between galaxies where the density of matter drops to nearly nothing and the light from any star takes millions of years to arrive, and the temperature of the background radiation has cooled to just under 3 degrees above absolute zero, there are particles drifting in states that no instrument has ever measured, and no conscious process has ever interacted with, carrying their quantum superpositions forward through time in a silence so complete that the word silence is not quite adequate to it, because silence implies the absence of something that was once present, and out there nothing was ever present to begin with. This chapter does not resolve what that means. It stays with it instead. The question that moves beneath this chapter without ever fully surfacing is this: does an unwitnessed superposition matter? Not morally, physically. Does the quantum state of a particle in the intergalactic void, one that has not interacted with anything complex enough to collapse it since, perhaps, the early universe, does that state participate in reality in the same way that a measured state participates? Or is it something else, something adjacent to reality, something that the physics describes with full mathematical confidence while the interpretation of what that description refers to remains genuinely open? This question is asked once. It will not be answered here. What the physics says is clear enough, at least at the level of the formalism. The wave function of an isolated particle evolves according to the Schrödinger equation regardless of whether anything is watching, regardless of whether the region it occupies is dense with matter and radiation, or empty beyond any terrestrial conception of empty. The equation does not require an observer. It does not have a term for witness. It simply describes how the quantum state changes over time, and the change it describes is continuous and deterministic and indifferent to the presence or absence of anything that might be called awareness. So the particle drifts. The wave function evolves. The superposition, if the particle was left in one by whatever last interaction shaped its state, persists through durations that stretch from the scale of human history into the scale of geological time and beyond, uninterrupted, untouched, carrying its open condition through the dark the way light carries itself, not toward anything, not away from anything, simply forward, because forward is what time does and the wave function follows. The light comparison almost forms here, almost becomes something to hold on to, but it is softer than a comparison, more like a proximity, a neighbouring image that doesn't quite touch the thing it's near. There is a version of quantum mechanics, associated most prominently with the Copenhagen interpretation, in which the question of what happens to an unobserved quantum system is not a question the theory is obligated to answer. Bohr's position, stated carefully, was that quantum mechanics is a framework for predicting the outcomes of measurements, and that asking what the system is doing in the absence of measurement is asking something outside the theory's jurisdiction. The theory is silent on the matter not because it is incomplete, but because the question properly understood is not well formed. There is no measurement, there is no outcome, there is nothing for the theory to predict. This is a coherent position. It is also, to put it plainly, deeply unsatisfying to a certain kind of mind, the kind that wants to know what is happening out there regardless of whether anyone is in a position to find out. The universe was doing things for 9 billion years before anything capable of asking questions about it existed anywhere within it, and the assumption that physical processes require some form of witness to be real in any meaningful sense strains against an intuition that feels close to bedrock. Though intuitions at the quantum scale have a poor track record, and that uncertainty about whether the dissatisfaction is reasonable or whether it reflects a bias built into minds that evolved at classical scales seems worth holding openly rather than resolving in either direction. Other interpretations do not stay silent. The many worlds interpretation, developed by Hugh Everett in 1957 and refined by others since, holds that the wave function never collapses at all. Not in the intergalactic void, not in the laboratory, not anywhere. Every quantum event that might produce multiple outcomes instead produces a branching of the universal wave function, with each branch continuing forward as a real physical history. The particle in the void does not need to be measured to have a definite state in some branch. Every possible state is definite in some branch. The universe is not waiting for a witness. It is continuously, silently proliferating its own outcomes without any external arbitration. The pilot wave interpretation takes a different approach. positing that particles always have definite positions guided by a real wave moving through space, and that the apparent randomness of quantum measurement reflects the statistical distribution of initial conditions rather than any fundamental indeterminacy. In this picture, the particle in the void has always been somewhere specific, moving along a trajectory determined by the pilot wave, and the superposition is a property of the wave rather than the particle itself. Both of these interpretations agree with every experimental prediction of standard quantum mechanics. Both of them give the particle in the void a definite physical status that the Copenhagen interpretation declines to grant. And yet neither of them has achieved consensus among physicists, not because their mathematics is flawed, but because the question of which picture is correct is not, currently, an empirical question. The predictions are identical. The realities they describe are irreconcilably different. What this means for the particle drifting between galaxies, whether it is in a genuine superposition with no fact about its state, or branching silently across many worlds, or riding a pilot wave through a definite trajectory, is a question that the particle itself, if particles could be said to have perspectives on such things, would have no way of answering. It drifts regardless. The space around it is not empty in the quantum field sense. The vacuum is threaded with fluctuating fields, virtual particles momentarily borrowing energy from the uncertainty principle before returning it, a constant low-level activity that is real in its physical consequences, even if nothing macroscopic is happening. But the particle, for the purposes of its quantum state, is isolated enough that coherence persists. The superposition holds. The wave function carries its open condition through a volume of space that no light from a human civilization has ever reached, and no instrument humanity has ever built could survive long enough to operate within. It holds, and nothing waits for it to resolve. Nothing notices that it hasn't. The darkness around it is not an absence of observation in any meaningful sense. It is simply the ordinary condition of most of the universe, which is vast and cold and largely indifferent to the interpretational debates of the small warm creatures on the third planet of a minor star in one of several 100 billion galaxies, each of which contains several 100 billion stars, around many of which particles of various kinds are drifting, in states that the physics describes and the philosophy cannot yet fully account for. This is not meant to diminish the question. It is meant to give it its actual scale, which is one of the things that looking outward tends to do to questions that felt manageable when they were first asked in a room. The particle drifts. Time passes in the way that time passes in places where nothing marks it, uniformly, without accumulation, without the quality that proximities to events gives time when events are actually occurring nearby. A second there is the same duration as a second here, in the sense that physics means when it uses the word duration, but it contains nothing that would make it distinguishable from the second before it or the one after, and in that undifferentiated flow, the wave function continues its quiet evolution, neither progressing toward collapse nor retreating from its open condition, simply continuing the way things that are not interrupted simply continue. The witnessed and the unwitnessed are not, in the mathematics, different things. The equation does not distinguish them. The wave function of the observed particle and the wave function of the unobserved particle evolve by the same rule. The difference lives in the interpretation, in the story told about what the mathematics refers to, in the question, asked once, left open, of whether the unwitnessed state participates in reality the way a measured state does, or whether participation requires something that the void by definition cannot provide. Out there, nothing answers. The particle carries its state forward into durations that have no name in any human language for the measurement of time, and the universe does not seem troubled by the fact that no one is checking. Whether that is reassuring or not depends perhaps on what you were hoping the universe would need from you, and the dark between galaxies continues in either case vast and patient and full in its own quiet way, of states that have never been asked to become anything in particular, which is where this chapter leaves things, not because the leaving is an answer, but because some conditions are more honestly described by staying with them than by moving through them toward something else. Something landed on a detector screen in the early 19th century that nobody was ready for, not conceptually. The mathematics would come later, the interpretation later still. The full strangeness not arriving in force until the 20th century had accumulated enough experimental precision to make denial impossible. But the shape on the screen was already there. Bands of light and dark alternating, produced by a single source of light passed through two narrow gaps in a barrier. The pattern was familiar from water, from sound, from every medium known to carry waves. It was not familiar from particles, and light at that point in history was being seriously considered as both. That tension never fully resolved, it just deepened. Feel the weight of something small in your hand, a grain of rice, a seed, something with edges, with mass, with a definite location in your palm. Now imagine throwing it at a wall with two narrow gaps cut into it, a gap just wide enough for the grain to pass through. It goes through one gap or the other. It lands somewhere on the other side. Do this 1,000 times and the pattern on the far wall is exactly what you'd expect. Two clusters, one behind each gap, the accumulation of 1,000 individual impacts, each taking one path or the other, each landing where the geometry says it should land given which gap it chose. This is the classical picture. Particles go through one slit. Waves go through both. Now send electrons instead. The electron gun fires them one at a time. This is the crucial detail, the one that makes everything strange rather than merely interesting. Not a beam, not a stream. One electron, then a pause, then another. Each electron arrives at the detector screen alone, with no other electron nearby to interfere with it. No wave in the classical sense moving alongside it. Nothing but the electron and the barrier and the two slits and the screen waiting on the other side. Each electron lands as a point, a single mark, particle-like localized, occupying one spot on the screen, with the decisiveness of something that has a definite position at the moment of arrival. And yet, build up the pattern over thousands of electrons, each one arriving alone, each one landing as a point, and the accumulated marks form an interference pattern. Bands of high density and low density, alternating across the screen, identical in structure to the pattern produced when a wave passes through both slits simultaneously, and the two resulting wavefronts overlap and reinforce or cancel each other depending on the path length difference. The electron, sent alone, somehow went through both slits. This is not a metaphor. This is not an approximation of what happened. The experiment has been performed with electrons, with photons, with neutrons, with whole atoms, with molecules containing dozens of atoms. And the interference pattern appears every time, as long as no measurement is made to determine which slit each particle used. The pattern is a physical fact recorded on a physical screen by physical impacts. The strangeness is not in the interpretation, it is in the data. What produces the interference is the wave function. The quantum mechanical description of the electron before it is detected spreads through space like a wave, passing through both slits, the two portions of the wave function overlapping on the far side, and producing regions where the probability of detection is high and regions where it is nearly zero. When the electron finally interacts with the screen, it does so at a single point, but which point is governed by the probability distribution that the wave function produced. and that distribution carries the signature of both slits even though only one electron was involved. The electron did not split. The electron is not a wave in the classical sense, not a disturbance in a medium, but it is also not a particle in the classical sense, not a thing with a definite trajectory that passed through one gap or the other while the physicist wasn't looking. It is something that the word particle was not designed to hold, something that the word wave was not designed to hold, something for which the language of the everyday world was never built because the everyday world never needed that kind of language to get through a Tuesday. Now, and this is where the strangeness becomes something more than strange, becomes something that touches the relationship between the physical world and the act of knowing. Put a detector at the slits, any detector, a device that will register which slit the electron passed through, that will answer the question without disturbing the electron more than the minimum that physics allows. Do this, and the interference pattern disappears, not weakens, disappears. The electrons, now detected at one slit or the other, begin landing in exactly the pattern you would expect from classical particles. 2 clusters, one behind each slit, no alternating bands, no interference. The act of acquiring the information about which path the electron took changed what the electron did. The knowledge collapsed the superposition. The open condition, through both slits, weighted by amplitude, carrying the distributed reality that produces interference, closed the moment the world acquired information about it. This is the part I keep returning to, not because it resolves into something comfortable, but because it doesn't. The detector doesn't need to be a conscious observer. It doesn't need to be a person or even a complex measuring device. Any physical interaction that leaves a record of which slit the electron used, any correlation between the electron's path and the state of anything else in the universe, is sufficient to destroy the interference. The information itself is what matters, not the awareness of it, not the reading of it, the existence of it, encoded somewhere in the physical world. And this arrives slowly, the way something true tends to arrive when you have been circling it rather than approaching directly. The realization that what the double-slit experiment is really showing is not that electrons are waves, not that electrons are particles, not even that electrons are both. It is showing that the boundary between a quantum system and its environment is not a fixed line but a dynamic condition. That openness, the capacity to be in superposition, to carry both paths simultaneously, is not a property of the electron in isolation, but a relationship between the electron and everything that is, or is not, entangled with it. The electron goes through both slits when nothing knows which slit it used. It goes through one when something does. Feel again the grain of rice in your hand, the weight of it, the pressure against your palm. You know exactly where it is. You know this because you're holding it, because your skin is pressing against it, because the interaction between the grain and your hand has established, with complete physical thoroughness, its location. That knowing, that physical correlation between the grain and your nervous system is classical. It happens at a scale where the quantum openness has already collapsed under the density of interaction, where the grain's quantum state decohered before your hand ever closed around it, where the question of which slit was never asked because there are no slits, only the continuous pressure of an environment so rich with interaction that no superposition survives long enough to be meaningful. But the electron in the experiment exists briefly in the absence of that density, in the careful quiet of a vacuum chamber, shielded and isolated, fired from a source that sends it alone. And in that quiet, it moves through the world the way things move when nothing is watching. Not with freedom exactly, but with a kind of latitude that the watched thing never has. It takes both paths because nothing has asked it to take one. The asking is physical. The answer is physical. What changes when the detector is added is not the electron's behavior in some subjective sense. What changes is the physical state of the world. The detector, by recording which slit, becomes entangled with the electron's path, and that entanglement collapses the superposition as thoroughly as any measurement made by any scientist in any laboratory. The electron doesn't know it's being watched. It simply responds as quantum systems respond to the fact of physical correlation. There was an afternoon, and calling it an afternoon is an approximation, a compression of years of experiment into a single image, when the pattern on the screen made it impossible to continue pretending that the question of which slit had an answer before it was asked. The bands were there, alternating, precise, built from the impacts of individual particles that had each of them passed through both openings in a wall. The afternoon has not ended. The experiment continues to be performed in laboratories around the world, refined and extended and applied to systems of increasing complexity, and the result is always the same. The pattern appears when nothing knows the path, the pattern vanishes when something does. And between those two conditions, the open and the closed, the both and the one, lies the entire architecture of quantum mechanics, waiting to be walked through, if not quite yet fully understood. Something in the physics decided, early on, that knowing costs something. What exactly it costs and where the payment goes and whether the ledger ever balances, these are questions that the pattern on the screen raises every time it appears and every time it disappears, and in the space between one electron arriving and the next one leaving the gun, when the screen holds whatever it held before and the next mark has not yet been made. There is a transaction at the center of quantum mechanics that has no equivalent in the world of ordinary things. Not a trade in the commercial sense, not an exchange with winners and losers, but something more like a structural feature of how information and physical reality are related at the smallest scales. A feature that the theory did not invent but discovered, in the way that geography is discovered rather than designed. The transaction goes like this. To know something about a quantum system is to change what that system is, not what we think it is, what it is. The knowing is physical, the cost is physical, and what is spent in the act of measurement does not return. This chapter follows what lingers after that transaction is complete. The central image here is a ledger, not a dramatic one, a quiet one, the kind kept in the back of a small business by someone who has been doing it long enough that the columns are filled in without ceremony. Income on one side, expenditure on the other. The balance maintained not because anyone is watching, but because the numbers require it. In quantum mechanics, something like this ledger exists, though the currencies it tracks are not money but certainty, and the rule it enforces is not accounting convention but physical law. The rule has a name, the Heisenberg uncertainty principle, and it is, in its actual content, rather different from its reputation. The uncertainty principle is often described as a statement about the limits of measurement, as though the problem were technological, as though a better instrument designed with more precision, more care, more ingenuity, could in principle push past the limits and recover the information that cruder tools leave obscured. This description is wrong, not slightly wrong, structurally wrong. The uncertainty principle is not about instrument precision. It is about the relationship between pairs of physical properties that are, in a technical sense, incompatible, properties that cannot simultaneously be well defined, not because we lack the tools to measure them simultaneously, but because the physical state itself does not contain simultaneous precision in both. Position and momentum are the canonical pair. The more precisely a particle's position is defined, the more tightly its wave function is localized in space, the more spread out its momentum becomes, the less certain its future trajectory. This is not a trade-off between two measurements. It is a trade-off within the state. The localization of position and the localization of momentum are mathematically inverse. A wave function cannot be narrow in both simultaneously. Sharpening one blurs the other, not as a consequence of the act of measurement, but as a consequence of what a wave function is. The ledger enforces this. Spend certainty on position, and the momentum column empties. Spend it on momentum, and position goes. The total is not conserved. This is not a conservation law in the usual sense, but the exchange is real, and it moves in only one direction at a time, and it cannot be undone without spending something else. What follows from a measurement, then, is not simply a number. A measurement of a particle's position, a real one, performed with a real instrument, leaves the particle in a state that is more localized in space than it was before, which means less localized in momentum, which means its future behavior is less predictable than it was before the measurement was made. The act of knowing where it is has made it less knowable in other ways. The information gained and the information lost are not independent. They are coupled by the structure of the theory, and the coupling is not approximate. It is exact. This consequence lingers. After the measurement is complete, after the instrument has recorded its value and the physicist has noted it down, the particle carries the mark of having been measured in the shape of its remaining uncertainty. It is not the same particle, not in any dramatic sense, not changed in kind, but changed in state, carrying a different distribution of possibilities than it carried before the interaction occurred. The measurement is over, its effects are not. There is a related consequence that operates at a different scale, one that connects the uncertainty principle to something more immediately physical. To measure a particle's position with high precision requires probing it with something whose own wavelength is very short. High-energy photons, for instance, whose short wavelength provides the spatial resolution needed to localize the particle. But high-energy photons carry significant momentum. When one of them scatters off the particle during the measurement, it transfers some of that momentum to the particle, disturbing it in a way that is not incidental but necessary. The very tool used to measure position imparts momentum uncertainty. Not because the tool is poorly designed, because the tool, to do its job, must interact with the system, and interaction always entails exchange. This is the physical mechanism underlying what the mathematics expresses abstractly. The principle is not just an equation, it is grounded in the way that probing something at small scales requires short wavelength, high-energy interrogation, and that interrogation inevitably disturbs the thing being examined. There is no gentle enough photon that can resolve a position precisely without kicking the particle into a broader range of possible momenta. The gentleness required would sacrifice the resolution. The resolution requires a roughness that spreads the momentum. The ledger closes either way. It seems worth pausing here, or rather it seems worth noting, since the chapter has been moving at a pace that doesn't naturally pause, that the uncertainty principle is sometimes taken as evidence that quantum mechanics is the theory of ignorance rather than a theory of reality. That the uncertainty is in us, not in the system. This reading has the relationship backward, or, no, perhaps backward is too strong. It has the emphasis misplaced in a way that matters. The uncertainty is in the state. The wave function before measurement is not hiding a definite position and a definite momentum behind a veil of our ignorance. It is a state in which definite position and definite momentum do not simultaneously exist. The uncertainty is ontological before it is epistemological. It is a feature of what the system is before it becomes a feature of what we know about it. The distinction is not academic. It determines what kind of thing quantum mechanics is. A theory of ignorance would imply that a better theory exists underneath, one in which particles have definite positions and momenta at all times, and the uncertainty reflects only our failure to access them. The Bell inequality experiments, discussed in an earlier part of this, showed that no such theory can reproduce the predictions of quantum mechanics while preserving locality and realism. The uncertainty is not a gap in our knowledge. It is a gap in the world, if gap is even the right word for something that is not an absence but a structural feature. The central metaphor of the ledger holds through all of this, but it begins to thin toward the end. A ledger implies that something is being preserved, that the total is conserved, that the columns balance. The uncertainty principle is not quite that tidy. What it enforces is a minimum product of uncertainties, not a fixed sum. The balance is not between what you know and what you don't, but between how precisely two complementary properties can simultaneously be defined. And as the chapter settles into its later motion, the ledger becomes less useful. Not wrong, but insufficient. The way any image eventually becomes insufficient when the thing it's describing is strange enough. The transaction remains. The cost is real. What is spent in acquiring knowledge about a quantum system changes the system, leaves a mark, shifts the distribution of what remains knowable. And the physicists who first understood this, Heisenberg in 1927, working through the mathematics in the quiet of Copenhagen, were not discovering a limitation of their instruments. They were discovering a feature of reality that had been there all along, operating at every scale, enforced by the structure of the universe with the quiet consistency of something that has never needed to announce itself, because it has never been otherwise. The ledger was always being kept, the entries were always being made, the universe was always spending certainty in one column to gain it in another, following rules that required no accountant and no oversight and no moment of decision, just the steady, unannounced arithmetic of a world in which knowing and being are not as separate as they appear from the comfortable distance of the scale at which humans live and move and ask questions about what is happening below them. The knowing costs something. The cost is structural, and the ledger, closed at the end of every measurement, opens again immediately, because the particle, changed by what was done to it, is already carrying a new set of possibilities forward into the next moment, waiting in the way that quantum things wait, which is to say not waiting at all, but simply continuing, open in the ways it is still permitted to be open, uncertain where certainty was the price of what was just learned, which is, more or less, where this began, with a transaction that leaves both parties changed, and a world that keeps its accounts in a currency that only resolves into ordinary numbers at the moment of asking. There is a property of the electron that has no home in the visible world, not a simplified version of something familiar, not a smaller instance of something large people can point to and say, yes, like that, but tinier. It is genuinely without analogue. Physicists gave it a name borrowed from rotation, and the borrowing was useful for the mathematics and misleading for the imagination. And both of those things remain true simultaneously, which is perhaps appropriate given the subject. The property is called spin. Begin with what spin is not. An electron is not a tiny sphere rotating on an axis the way the Earth rotates, carrying its surface around at some angular velocity, generating a magnetic field through the motion of its charge. This picture was tried. It fails immediately upon contact with the numbers. The electron would need to be rotating faster than the speed of light at its surface to produce the magnetic moment it actually has. And since the electron has no known size in the classical sense, the surface in question doesn't meaningfully exist anyway. The spinning top model is intuitive. It is wrong. And the wrongness is not a minor inaccuracy to be corrected with better modelling. It is a signal that the property being described does not belong to the category of things that spin in any ordinary sense. What spin actually is a quantum number, an intrinsic property, like mass or charge, that the particle simply has, not because it is doing something, not because something is rotating, but because that is what the particle is. An electron has spin 1/2. This means that when its spin is measured along any axis, the result is always one of two values, positive 1/2 or negative 1/2, in units of the reduced Planck constant. Up or down, relative to the direction of measurement. Always one of those two. Never anything in between, never a continuous range of values, never the smooth spectrum of outcomes that a genuinely rotating classical object would produce depending on the angle of its axis relative to the measurement direction. The strangeness deepens if you try to hold the geometry of it. Imagine measuring the spin of an electron along the vertical axis and finding it to be spin up. Now rotate your measurement device 90 degrees and measure again. The result is again either up or down, but now up and down mean something different, because the axis has changed. The electron's spin state relative to the new axis is in superposition, the earlier definite value of spin up along the vertical becoming a combination of spin up and spin down along the horizontal, with equal probability of yielding either outcome. The certainty in one direction dissolved into uncertainty in another, following the same logic that governs position and momentum but now applied to orientation, to the directions in space along which a property can be asked about and will produce an answer. How is this like anything? It isn't, quite. The closest thing is perhaps a conversation that produces different answers depending on what language it is conducted in. Not because the person speaking is hiding something or being inconsistent, but because the question itself shifts meaning, depending on the frame of the asking. But that comparison is loose, and the looseness is the honest part of it. The acknowledgement that the thing being described is not a harder version of something familiar, but a different kind of thing entirely. What makes spin more than a curiosity? What gives it weight beyond the philosophical interest of a property with no classical home? Is that it is real in ways that are physically consequential. The Stern-Gerlach experiment, conducted in 1922 by Otto Stern and Walter Gerlach, sent silver atoms through a non-uniform magnetic field and recorded where they landed on a detector plate. Classical physics predicted a continuous smear. Atoms with their magnetic moments oriented at various angles would be deflected by various amounts, producing a smooth distribution on the plate. What appeared instead were two discrete bands. Two, and only two. The magnetic moment of the silver atom, it turned out, was dominated by the spin of a single unpaired electron, and that spin could only be detected in two states, not a continuous range. The discreteness was there before anyone had the theoretical language to explain it. The experiment produced the result, and the result waited for the theory to arrive and give it a name. Spin arrived in theoretical form through the work of Wolfgang Pauli and later Paul Dirac, whose relativistic wave equation for the electron produced spin as a mathematical necessity, not an assumption, not an additional postulate, but a consequence of combining quantum mechanics with special relativity. The electron had to have spin 1/2. The equation demanded it. This was one of the moments in physics where mathematics, pushed into a new regime, returned something that the physical world had already quietly been doing without waiting for permission. The superposition of spin states is not a secondary feature. It is the condition from which measurement extracts a definite value, and the extraction is, as always, irreversible in a particular direction. Before the measurement, the electron in a general spin state carries both possible outcomes with specific probability amplitudes, complex numbers whose squared magnitudes give the likelihood of each result, whose relative phases govern how the spin state transforms when the measurement axis is rotated. After the measurement, the spin is definite along the measured axis, but it is now indefinite along every perpendicular axis, the certainty in one direction purchased at the cost of openness in all others. This is the layering that makes spin quietly vertiginous to think about for too long. Is that the right word? Vertiginous? Maybe it is more like standing at the edge of something that has no visible bottom, not frightening but genuinely open downward in a way that ordinary ground is not. A particle with definite spin along one axis has a completely indefinite spin along any perpendicular axis. It is not that the perpendicular spin is hidden, it is that the perpendicular spin is genuinely undetermined, carrying all possible values with the probabilities that the quantum state assigns, waiting for a measurement along that axis to produce one of them, at which point the original axis becomes indefinite again. The electron does not have a spin, it has a spin state, and the state depends on the question being asked of it. There is an additional fact about spin that seems, on first encounter, like an abstract mathematical detail and reveals itself on further contact to be one of the stranger things in all of physics. Particles with half-integer spin, electrons, protons, neutrons, quarks, all the matter particles, require a rotation of 720 degrees to return to their original state. Not 360, not one full rotation, 2 full rotations. If you rotate the spin state of an electron by 360 degrees, you do not get the original state back. You get the original state multiplied by -1, which is a different quantum state, even though it produces the same measurement probabilities. It takes another 360 degrees, a full second rotation, to return to where you started. There is no everyday object that behaves this way. No top, no planet, no wheel. A full rotation of anything at human scale returns it to its starting condition. The electron's spin state requires 2 full rotations. This is not a visualization problem or a failure of imagination. It is a fact about the topology of the space of quantum states, a deep geometric property of the mathematical structure underlying matter, visible in physical consequences like the Pauli exclusion principle, which governs why matter is solid, why atoms have the structure they do, why the table you might be lying near right now does not allow your arm to pass through it. The solidity of the world is, in part, a consequence of a rotation property of particles that no human hand has ever directly observed. This chain of consequence, from the abstract geometry of spin space to the tangible resistance of matter, is either beautiful or simply true, and those may not be different things, though the question of whether that distinction matters is one that keeps moving without arriving anywhere settled. Spin is still being used. In MRI machines, nuclear magnetic resonance technologies probe the spin states of hydrogen nuclei in tissue, using the quantum behavior of spin, its discrete values, its precession in magnetic fields, its predictable response to radio frequency pulses, to produce images of soft tissue that no other non-invasive technology can match. The hospital, the scanner, the image of a brain or a knee or a spine, all of it downstream from the experiment in 1922 that showed 2 bands on a plate where a smear was expected. The spin that has no classical home turns out to have many practical addresses. It lives in the detector, in the magnet, in the software that reconstructs the image, in the diagnosis that follows. It operates without anyone in the room needing to understand its strangeness. It simply works, the way the deep properties of the world tend to work, quietly, consequentially, indifferent to whether the people benefiting from them have spent any time thinking about what it means for a particle to need 2 full rotations to return to itself. What it means is a question that trails off rather than resolves. Something about the relationship between mathematical structure and physical fact, between the abstract symmetries of quantum theory and the concrete resistance of a table or a wall or the ground. And the answer, if it is coming, has not arrived yet in any form that closes the question without opening several more beside it. The world does not feel quantum mechanical. This is the first fact, and it is worth sitting with before anything else is said, because it is both completely true and completely strange. True in the sense that the macroscopic environment operates according to rules that look nothing like superposition or wavefunction or probability amplitude. Strange in the sense that the macroscopic environment is made, without exception, of things that do obey those rules. Every atom and electron and photon in every object you have ever touched, governed by the same quantum mechanics that produces interference patterns and spin superpositions and entanglement across vast distances. And yet the objects themselves, the chair, the wall, the ground, behave with the solidity and a determinacy that quantum mechanics, taken naively, does not seem to predict. Something happens between the quantum and the classical, something that is not a wall and not a boundary, and not a moment of transition but a process, continuous and ubiquitous and so fast at ordinary scales that it is effectively invisible, producing classical reality out of quantum possibility the way a river produces a delta, not by any single event but by the accumulated consequence of countless small interactions, each one nudging the system further from openness, until the openness is gone and only the classical appearance remains. That process is decoherence. Begin with a single quantum system in superposition, an atom, perhaps, in a superposition of 2 energy levels, carrying both possibilities simultaneously with the coherence that allows quantum interference to operate between them, the definite phase relationship between the components of the wave function intact and functional and doing the work that superposition does when it is left undisturbed. The system is isolated. Nothing surrounds it. The superposition holds. This is the starting condition, and it is also the condition that almost never obtains in the physical world outside of carefully engineered laboratory environments, because the physical world is not empty and not quiet and not willing to leave anything entirely alone for very long. Now introduce the environment, not dramatically, not as a disruption, simply as what is already there. The ambient photons threading through the space around the atom, the background radiation left over from the early universe, the thermal vibrations of whatever material might be nearby, the electromagnetic fields generated by every other charged particle within range of interaction, which is, in principle, every other charged particle in the universe, though the influence falls off with distance and the nearby environment dominates entirely. The environment is not hostile, it is simply present, in the dense and inescapable way that the environment at any ordinary location in the world is present. Each interaction between the system and the environment is small. A photon scatters off the atom. A thermal fluctuation perturbs its energy level slightly. A stray electromagnetic field applies a momentary nudge. Each of these events is, individually, a kind of measurement, not a conscious one, not one involving any instrument or any physicist, but a physical interaction that establishes a correlation between the state of the atom and the state of the environment, encoding a small piece of information about the atom's condition into the surrounding world. This is where the unravelling begins, and it happens not through collapse, but through entanglement, which is the gentler and in some ways more complete version of the same transition. When the atom interacts with an environmental photon, the two become entangled. The quantum state of the combined system is no longer separable into a state for the atom and a state for the photon independently, but is instead a joint state in which each possible condition of the atom is correlated with a corresponding condition of the photon. The superposition does not disappear from the combined system, it spreads into it. The atom-photon system now carries the superposition across two particles rather than one. Then the photon interacts with something else. Then that something else interacts with something further. The entanglement propagates outward through the environment like a ripple, each new interaction extending the web of correlation, each new particle added to the entangled system carrying a portion of the original superposition's information further from its source, diluting it across an ever larger number of degrees of freedom until the information is, for all practical purposes, irretrievable. Not destroyed, irretrievable. The coherence, the definite phase relationship that allowed the superposition to produce interference, is gone from the atom, not because it was eliminated, but because it is now distributed across an environment too large and too complex, and too constantly changing to be assembled and reversed. The atom from the outside looks classical. Its superposition has become effectively a classical probability distribution. The probability of finding it in one energy level or the other is still there, still calculable, still meaningful. But the quantum interference between the possibilities is gone, washed out by the decoherence, and what remains behaves exactly as a classical mixture would behave, as if the atom were in one state or the other, but we simply didn't know which. Number. Perhaps that's not quite it, because saying it behaves as if we simply didn't know which restores the old framing, the epistemic reading of quantum uncertainty, the idea that the probability is in the observer rather than the system, and decoherence does not quite vindicate that reading, even though it produces something that resembles it from the outside. The difference is subtle but real. In a genuine classical mixture, the system was always in one state or the other. The probability reflected ignorance. After decoherence, the system was in a genuine superposition that has spread into the environment, and the appearance of a classical mixture is produced not by pre-existing definiteness, but by the loss of the phase information that distinguished the quantum superposition from the classical mixture. The histories are different. The present appearance is the same. This distinction matters for the measurement problem, the deep question of why quantum measurements produce definite outcomes rather than superpositions of outcomes, and decoherence addresses it without fully resolving it, which is the honest description of what decoherence does and does not accomplish, and seems worth stating plainly rather than softening into false resolution. The timescales are what make this feel less like physics and more like inevitability. For a dust particle in ordinary air at room temperature, the decoherence time, the time it takes for quantum coherence to be effectively destroyed by environmental interaction, is estimated to be on the order of 10 to the negative 31 seconds. This is not a long time. This is not a short time in the way that a millisecond is a short time or even a nanosecond. It is a duration so brief that no physical process we can describe or measure operates on that timescale. The dust particle has never in any meaningful sense been in a quantum superposition at human accessible scales. By the time any measurement could be contemplated, the decoherence has been complete for longer than the age of the universe many times over. For a single ion trapped in a vacuum and cooled to near absolute zero, the decoherence time stretches to seconds or minutes. This is why quantum computers require such extreme conditions, not because the quantum behavior is fragile in any dramatic sense, but because the environment is relentless. And maintaining coherence means holding off the environment's intrusions long enough for the computation to proceed. The engineering required is extraordinary. The principle being exploited, that decoherence is a process with a timescale that depends on the system's size and the environment's temperature and density, is the same principle that makes classical objects classical without any engineering at all. There is something in decoherence that resolves the cat, at least partially. Schrödinger's complaint was that quantum mechanics, taken to its logical conclusion, predicts a cat in superposition, alive and dead simultaneously. Decoherence explains why this superposition, even if it began to form, would collapse into classical behavior in a time so short that it could not be distinguished from instantaneous. The cat is large, the cat is warm, the cat is embedded in an environment of extraordinary richness, the air around it, the photons bouncing off its fur, the thermal radiation it emits, the gravitational field it sits in, and every one of these environmental interactions is a decoherence event, a small entanglement that carries a piece of the system's quantum information outward into the world. By the time the quantum event in the box has had any macroscopic consequence, decoherence has already converted whatever superposition existed into something classical. The cat is one thing, not because observation collapsed the wave function, because the environment did. This is clean. It is satisfying in the way that mechanisms are satisfying. It gives the process a physical cause rather than a philosophical one, grounds the classical world in quantum dynamics rather than in the mysterious act of measurement, removes the observer from the center of the story, and it is genuinely correct as far as it goes. How far it goes is the part that remains uncertain. Decoherence explains why we never see superpositions at macroscopic scales. It does not fully explain why measurements produce single outcomes, rather than entangled superpositions that include the measuring device and the physicist and the laboratory. The wave function of the combined system, measured particle, detector, observer, is, after decoherence, enormously complex and spread across the environment, but it is still, in principle, a wave function, and wave functions do not, in the formalism, produce single outcomes by themselves. They produce distributions. Something else is at work in the final step, and what that something else is remains the measurement problem, still open, still unresolved by decoherence alone, despite what is sometimes claimed in simplified accounts. The end of openness, then, is not a wall but a gradient, not a moment but a duration, not a decision but an accumulation. Quantum systems lose their coherence the way a voice loses its distinctness in a crowded room, not cut off, not semiad, but absorbed, surrounded, overwhelmed by the density of everything else until it is no longer distinguishable from the background. The information is still there, in principle distributed across the correlations between every particle that participated in the decoherence process. It is simply beyond any conceivable recovery. The world feels classical because it is classical, at the scales where it is experienced, because decoherence operates so fast and so completely at those scales that the quantum substrate beneath is effectively sealed off from any ordinary access. The ceiling is not imposed from outside, it is self-generated, arising from the density of interaction that is simply the normal condition of existence in a warm, matter-filled universe. Underneath, the quantum mechanics continues. Every electron still has its spin, every photon its polarization, every atom its energy levels and transition probabilities. The rules do not change at the boundary between quantum and classical. The boundary is not a boundary. It is a region in which decoherence has been so thorough for so long that the question of what remains quantum about the system is no longer a practical question but a theoretical one, answerable in principle, inaccessible in practice, and pointing quietly toward the fact that the solidity of the everyday world is not a given but a consequence, produced continuously by a process that has no interest in being noticed and requires nothing from the world above it except the ordinary density of matter and the ordinary passage of time. The mistake is easy to make. Something about the way the mind works, the way it moves through possibilities one at a time, checking them off, entertaining each option briefly before setting it aside and picking up the next, makes superposition feel like alternation. As if the particle visits each possible state in sequence, flipping between spin up and spin down so rapidly that any measurement catches it mid-cycle and reports whatever it happens to be in that instant. As if the openness is really just speed. As if underneath the particle is always one thing, only one thing, and the quantum indeterminacy is a strobe effect rather than a genuine condition. This is wrong, and the wrongness is not incidental. Alternation requires time. If a particle were flickering between spin up and spin down, there would be moments of spin up and moments of spin down, each with some duration, each in principle detectable if the measurement were fast enough. The flickering model makes a prediction. Measure quickly enough, and you catch the particle in a definite state that it would have been in even without measurement. The statistics of outcomes would reflect the proportion of time spent in each state, not a fundamental probability. The particle would have a hidden history. The Bell inequality tests, described in an earlier chapter, ruled this out, not approximately, not statistically. The correlations between entangled particles measured at separate locations exceeded the limits that any alternation model, any model in which particles carry definite values even when not measured, can produce. The violations are large enough and the experiments are careful enough that the conclusion is not in serious dispute among physicists who work with the data. The particle does not alternate. It does not visit states. It occupies a condition in which multiple outcomes are simultaneously present, not in sequence but in structure. The right frame is not temporal, it is mathematical. A quantum state in superposition is a vector in a high-dimensional space called a Hilbert space. The possible measurement outcomes correspond to particular directions in that space, basis vectors in the technical language. A state in superposition points in a direction that is neither one basis vector nor another, but a combination, a direction that has components along multiple axes simultaneously. The components are not visited in order. They coexist. The vector points where it points, and the pointing is not a rapid oscillation between other directions, but a single orientation that simply is not aligned with any one measurement outcome. When a measurement is made, the state is projected onto one of the basis vectors, one of the possible outcomes, and that projection is what the detector records. The probability of each outcome is determined by how much of the original vector lay along that direction, which is the squared magnitude of the corresponding component. The process is not a discovery of which state the particle was secretly in. It is a physical interaction that selects one component and discards, or more precisely, entangles away, the others. This is where the hesitation enters, because the word discards is not quite right, and saying so without replacing it with something equally misleading requires a moment of care. The other components of the superposition do not disappear in any verifiable sense. In the many worlds interpretation, they continue in other branches of the universal wavefunction. In decoherence-based approaches, they become entangled with the environment and are no longer accessible to the local system, but are not destroyed. Even in the Copenhagen framework, which declines to speak about what happens to the components not selected, the formalism does not contain a mechanism for elimination. The collapse is imposed as a postulate, not derived from the dynamics. What happens to the unchosen possibilities is, genuinely, one of the unresolved questions at the center of quantum foundations. So, the measurement selects. What the selection does to the rest is less certain than the first part of that sentence implies. A useful distinction exists between coherent superposition and incoherent mixture. The difference is not visible in the probability distributions for a single measurement. Both a particle in superposition and a particle drawn randomly from an ensemble of definite states can produce the same outcome statistics if only one type of measurement is performed. The difference becomes apparent when interference experiments are run. A coherent superposition produces interference fringes, the alternating bands of high and low probability seen in the double slit experiment, because the components of the superposition have a definite phase relationship, a precise mathematical synchrony that allows them to reinforce or cancel each other depending on the geometry of the experiment. An incoherent mixture produces no such fringes. The phase information is absent. The states have been randomized in a way that destroys the synchrony, and without synchrony, interference cannot occur. This distinction is what decoherence destroys, not the probability distribution, not the individual outcomes, the phase relationship, the synchrony. And without it, the superposition becomes, for all measurable purposes, equivalent to the classical mixture that the mind reaches for instinctively when it tries to picture what quantum indeterminacy means. The instinctive picture is not wrong at that stage, but it comes after the coherence is lost, and the loss is the step that does the work. The simultaneity of superposition is not something the brain was built to hold in any direct way. This seems worth saying plainly, not as an apology for the difficulty, but as a description of its source. The brain evolved to track objects at human scales, where decoherence has already done its work, where the simultaneous possibility condition of quantum states has already collapsed into the single outcome reality of classical objects. The cognitive equipment available for picturing the physical world was shaped by selection pressures that had nothing to do with quantum mechanics, because quantum mechanics at human scales produces classical behavior, and classical behavior was all that needed to be navigated for survival. The quantum world was simply never visible from where evolution happened. So the mind reaches for alternation, because alternation is something it can picture. The particle flickers, the coin spins, the system oscillates between options at high speed, and the measurement catches a snapshot. This is the picture, and it is wrong, but wrong in the direction of something that the mind can hold, which is why it persists even among people who understand the correct description mathematically. The correct description is geometric, not temporal. The state is a vector. The vector has components. The components coexist in mathematical space without visiting each other, without taking turns, without any temporal process connecting them. They are simultaneously present in the only sense the formalism provides, which is also the only sense that the experimental results require. Consider how this applies to something slightly larger. Not a single electron, but a small molecule, a few atoms bound together, placed in a superposition of two vibrational states. Each vibrational state corresponds to a different pattern of atomic motion within the molecule, a different distribution of energy among the bonds and angles that hold it together. The superposition contains both patterns simultaneously, not alternating between them, not the molecule vibrating one way and then the other in rapid sequence. Both patterns present in the quantum state with definite amplitudes and a definite phase relationship between them, producing a combined condition that is neither vibrational state individually, but something that contains both, and that will, if an interference measurement is made before decoherence intervenes, show the signature of that containment. Experiments with small molecules have observed precisely this. Coherent superpositions of vibrational states, prepared with ultra-fast laser pulses and probed before the thermal environment has time to wash out the coherence, produce interference signals that confirm the simultaneous presence of both components. The molecule was in both vibrational patterns at once, not quickly alternating, genuinely both. As the molecule grows larger, coherence times shorten. The environment encroaches faster. The window during which the simultaneous condition can be verified narrows until it closes entirely. But the principle does not change with size. The physics that applies to the electron applies to the molecule. The simultaneity is there at every scale. The accessibility of it is what changes. There is something almost restful about this, once the initial strangeness passes. The particle is not anxious about its superposition. It is not holding itself in two states through effort. It is simply in a state that the mathematics describes and the experiments confirm, continuing forward through time according to the Schrödinger equation, the components of its superposition evolving in their definite phase relationship, neither one more real than the other, neither one waiting for permission to become the answer. The restfulness is not a metaphor, or if it is one that fades as the physics becomes clearer, because the clearer description has no need of restfulness or anxiety or any other quality borrowed from the experience of being a mind that holds things sequentially. The particle simply is what it is. The superposition is the state evolves, the components coexist. Simultaneity, in quantum mechanics, is not a paradox to be resolved. It is a description to be absorbed, slowly, without forcing it into a shape the mind already has, allowing it to remain the shape it actually is, which is geometric and mathematical and real, in the only sense that experimental confirmation provides. What follows from that reality, the consequences that spread outward when simultaneous states meet the world that is not yet entangled with them, is where the next portion of this will find itself, without urgency and without a fixed destination, drifting in the direction the physics points. The wave function is not visible. There is no instrument that displays it directly, no screen on which it appears, no photograph that captures its shape. It is a mathematical object, a function that assigns a complex number to every point in the configuration space of a quantum system, encoding the probability amplitudes for every possible measurement outcome, evolving forwarded in time according to the Schrödinger equation, with the kind of smooth determinism that makes the pre-measurement world look almost classical from the inside. It touches nothing in the way that physical things touch each other. And yet its reach is real, its influence is measurable, and the consequences of where it spreads determine everything that happens when a quantum system meets the world. Think about air, not the idea of air, but the actual thing, the way it occupies every part of a room without declaring itself, pressing against surfaces with a pressure that is constant and unremarkable, filling the space between objects so completely that the objects themselves seem to float in something rather than sit in nothing. Air is not noticed until it moves, until wind makes it directional, until absence makes it apparent. The wave function has something of this quality, not a direct comparison, just a proximity, present everywhere the mathematics says it is present, which may be spread across an enormous region of space, touching every location with some non-zero probability amplitude, occupying the geometry of the possible rather than the geometry of the actual. For a free electron moving through empty space, the wave function spreads. Given enough time with no interaction, no boundary, no potential energy landscape to confine it, the electron's wave function disperses outward from whatever region it was initially localized in, the probability of finding the electron becoming more diffuse as the wave function covers more territory. The electron has not moved to a new location. Its location has simply become less defined. the probability spread thinner across a larger region, the peak of the distribution flattening as the wings extend. Left long enough, the wave function could, in principle, span distances that exceed any human intuition of where a single particle should be. This spreading is not a malfunction. It is what the Schrödinger equation predicts for a free particle, and it is correct. The equation governs the time evolution of the wave function with precision, and the precision is not approximate. Quantum electrodynamics, the fully relativistic version of quantum mechanics applied to electrons and photons, is the most precisely tested theory in all of physics, with predictions confirmed to more than 10 decimal places. The wave function, for all its mathematical abstraction, is tracking something real. What exactly it is tracking, whether it represents the actual physical state of the world or only our knowledge of that state, whether it is ontological or epistemic, is the question that the interpretations disagree about and that no current experiment can resolve. What the wave function does, regardless of interpretation, is this. It carries the probability structure of all possible futures forward through time. It encodes at every moment the full distribution of what could happen next. And when the particle reaches a potential energy landscape, a barrier, a well, a boundary of some kind, the wave function responds to it. The response is wave-like. The wave function partially reflects from a barrier and partially transmits through it, with the transmitted portion potentially appearing on the far side of a barrier that classical mechanics would say the particle cannot cross. This is tunneling, and the wave function makes it not just possible but calculable. The transmission probability can be derived directly from the shape of the barrier and the energy of the particle. The reach of the wave function is most dramatically visible in entanglement. When two particles interact and become entangled, their wave functions, or rather the wave function of the combined system, can no longer be written as a product of two independent functions, one for each particle. The combined state is irreducibly joint. Measuring one particle immediately constrains what can be found when measuring the other, regardless of the distance between them. The wave function of the combined system is not located at one particle or the other. It is a function over the configuration space of both simultaneously, a space that has dimensions for each particle's position, and the correlations it encodes are non-local in a way that has no classical explanation. This is what troubled Einstein deeply enough that he spent years trying to show it was incomplete. The paper he wrote in 1935 with Boris Podolsky and Nathan Rosen, the EPR paper, argued that if quantum mechanics predicted these non-local correlations, and if local realism held, then the wave function must be an incomplete description of reality. There must be more beneath it, hidden variables not captured by the formalism. The argument was careful and the intuition behind it was reasonable, and it lost to Bell's theorem and the experiments that followed, in the way that careful, reasonable arguments sometimes lose to a universe that has its own preferences. The wave function touches both particles, not simultaneously in a way that sends information. The correlations cannot be used to communicate faster than light, and the proof of this is built into the formalism. But the joint state is real, the connection is real, and measuring one end of it changes what the wave function says about the other, instantaneously, across whatever distance separates them. Is the wave function itself real, a physical field propagating through configuration space, or is it a representation of knowledge, a bookkeeping device for tracking probabilities? This is the question asked once here, without an answer to follow it. The pilot wave interpretation answers yes, the wave function is real, a physical field that guides particles along definite trajectories. The many worlds interpretation answers yes in a different way. The wave function is the totality of physical reality, An apparent collapse is just the local appearance of a branching that is globally smooth. The Copenhagen interpretation declines to answer, on the grounds that the question exceeds what the theory is designed to address. Epistemic interpretations, cubism among them, answer no. The wave function is an agent's encoding of expectations, not a description of anything outside the agent's experience. All of these produce identical predictions. All of them agree on what the wave function does. None of them agree on what it is. There is something almost, not quite strange, but slightly vertiginous about a central object in a physical theory whose nature remains genuinely contested among experts in that theory. It seems from the outside as though this ought to have been resolved. The theory works, the predictions land, the technology built on the predictions functions in hospitals and laboratories and computing systems, and at the center of it, a mathematical object of disputed ontological status continues to evolve according to its equation, touching every point it reaches with a probability amplitude producing interference when its parts overlap, guiding particles toward their eventual measured outcomes through a mechanism that the formalism describes without fully explaining. The wave function touches the barrier. Part of it reflects, part transmits, the transmitted part spreads into the far region. Later, a detector in that region clicks, or it doesn't, with probabilities that the wave function specified in advance. The click is real. The number it reports is real. What was moving through the geometry between the source and the detector? Well, that is where the interpretations begin to diverge, and where this chapter leaves the thread hanging, not because the answer is unavailable, but because the available answers are many, and choosing between them tonight in the quiet does not seem necessary. The wave function continues forward regardless, deterministic until it isn't, open until something closes it, reaching always into the space of what could happen next. The numbers are agreed upon. Every working physicist who uses quantum mechanics agrees on what the theory predicts. Feed in the initial conditions, apply the formalism, extract the probability distribution for measurement outcomes. The procedure is unambiguous, and the results are correct to a precision that no other physical theory has matched in the history of science. The agreement on predictions is total. The agreement on what the predictions mean, that is something else entirely. 5 interpretations, not 5 guesses. 5 fully developed frameworks, each internally consistent, each reproducing every experimental result quantum mechanics has ever produced, each describing a fundamentally different universe. This is unusual. In most areas of physics, interpretational disagreement resolves when experiments become precise enough. The geocentric and heliocentric models disagreed on predictions. Galileo's observations settled it. Newtonian gravity and general relativity disagree on predictions in extreme conditions, the bending of light around massive objects, the precession of Mercury's orbit, the existence of gravitational waves, and the experiments confirmed Einstein. The interpretations of quantum mechanics do not disagree on predictions. They are in the technical sense empirically equivalent. No experiment currently conceivable can distinguish between them, because they were constructed to be indistinguishable, or because the differences between them, if they exist, live at scales or in regimes that no instrument yet reaches. So the disagreement persists, not from laziness, not from insufficient thought, from genuine underdetermination, the situation where the evidence, complete as it is, does not uniquely fix the theory. Copenhagen first. The oldest, the most widely taught, the one that most physicists encounter first and many never fully leave. Associated with Niels Bohr, though Bohr's actual position was more nuanced than the textbook version suggests. The core claim, quantum mechanics is a complete theory of measurement outcomes. The wave function describes the probabilities of what will be found when a measurement is made. What the system is doing between measurements is not a question the theory answers, and insisting that it must answer it is a category error. Importing classical assumptions about continuous objective reality into a domain where those assumptions no longer apply. The wave function collapses upon measurement, not because something physical happens to collapse it. Copenhagen is deliberately silent on the mechanism, but because the description updates the way a probability distribution updates when new information arrives. The theory is about knowledge, about what can be predicted and verified. The question of what is real beneath the predictions is not a scientific question. It is, Bohr suggested, a question that the structure of quantum mechanics itself reveals to be malformed. This is a coherent position. It is also, to say it plainly, unsatisfying in a way that feels permanent rather than temporary. The silence on mechanism is not a placeholder awaiting better understanding. It is a deliberate boundary, and some minds find boundaries in places where explanation should be less a feature than a refusal. Many worlds arrives next, and it arrives with a different problem entirely, not insufficiency but excess. Hugh Everett proposed in 1957 that the wave function never collapses, ever. The Schrödinger equation applies universally, without exception, including to the measuring device and the physicist and the laboratory, and everything else involved in any measurement. When a quantum event with two possible outcomes occurs, the wave function does not select one. It branches. Both outcomes occur in separate, non-communicating branches of the universal wave function. Every quantum event that has ever happened has branched the universe in this way, producing an enormously, perhaps infinitely large number of parallel histories, each as real as the one being experienced here. The appeal is the universality. No collapse postulate, no special role for measurement, no observer-dependent reality, just the Schrödinger equation, applied without exception, forever. The cost is the branches, all of them, real, unobservable from within any given branch. The ontological extravagance required is something that reasonable people find either trivially acceptable or deeply troubling, and the line between those two reactions does not seem to track expertise in the physics. It tracks something else, a prior about what kinds of theoretical commitments are acceptable, what counts as explanatory, whether unobservable entities incur a theoretical debt. Pilot wave theory, de Broglie's original idea developed into a complete framework by David Bohm in 1952, offers a third picture. Particles always have definite positions. Always. The wave function is a real physical field that guides them, determining their trajectories through a dynamics that reproduces quantum statistics exactly. Measurement outcomes are determined by the particle's actual position at the moment of measurement, and the apparent randomness of quantum mechanics reflects the statistical distribution of initial positions across an ensemble. Not fundamental indeterminacy, but epistemic uncertainty about initial conditions, the old kind of probability, the kind that lives in the observer rather than the system. Hidden variables, then, the kind Einstein wanted. But local hidden variables were ruled out by Bell's theorem. Bohm's theory preserves determinism by abandoning locality. The pilot wave is non-local. The guidance it provides to a particle can depend on the state of an entangled partner arbitrarily far away. This non-locality is real and unavoidable, and it raises questions about compatibility with special relativity that the theory has not fully resolved. And then cubism, quieter, stranger in a different direction. The wave function in cubism is not a description of the physical world at all. It is an agent's personal encoding of beliefs about the outcomes of future experiences. When a measurement is made and the wave function updates, this is not collapse, It is Bayesian belief revision, the ordinary updating of a probability distribution in response to new information. The theory is about the interface between an agent and a world that the agent cannot fully describe from the outside. Cubism is not idealism. It does not deny that a physical world exists. It denies that quantum mechanics, correctly understood, is a description of that world from a view from nowhere. It places the agent irreducibly inside the picture, and it finds in this placement not a limitation but an honest acknowledgement of what any physical theory actually is. A tool used by agents embedded in a world to navigate their experience of it. Here is where the hesitation settles in before any conclusion forms. Because the honest position sitting with all four of these frameworks, and there are others, relational quantum mechanics, consistent histories, each with its own careful architecture, the honest position is that none of them is obviously right and none of them is obviously wrong, and the choice between them is not currently a scientific choice in the experimental sense, but something closer to a philosophical preference, a decision about which kinds of explanatory commitments feel more fundamental, which kinds of ontological costs are worth paying for which kinds of theoretical virtues. This is personally one of the more remarkable situations in all of science, a theory that works better than any other. A century of experiments confirming its predictions, and at its foundation, a genuine unresolved disagreement about what it is describing. Not what it is missing, what it is doing, what the wave function refers to, whether collapse is physical or epistemic, whether the branches are real, whether particles have positions when no one is looking. The data does not answer these questions. The questions were constructed in part to be immune to the data available. Whether future physics, some deeper theory, some currently unimagined experiment, will break the equivalence and force a choice is unknown. It might. Or the interpretational plurality might persist, a permanent feature of the landscape, a set of maps that all describe the same territory with equal accuracy and irreducibly different cartographic philosophies. The numbers remain agreed upon. The predictions land. The technology functions. The disagreement at the center continues, carried forward by physicists who understand the formalism completely and still cannot agree on what they are looking at when they write down the wave function and watch it evolve, which is perhaps closer to an honest picture of scientific knowledge than the cleaner version usually offered. Not a set of settled facts, but a live frontier, inhabited by careful people holding different maps of the same confirmed terrain, each map useful, none complete, all pointing at something the territory itself has not yet finished revealing. And the wave function continues to evolve, indifferent to the disagreement about its nature, doing whatever it does between the measurements that everyone agrees on, in the silence where the interpretations live. Put your hand on something near you, a blanket, a pillow, the edge of a mattress. Feel the resistance, the pressure back against your palm, the temperature of it slightly warmer now where your skin has been resting. The material conducting heat away from you, at a rate that registers as neither cold nor warm, but simply present, simply there. A surface doing what surfaces do when a body meets them in the dark. That resistance is real. The solidity is real. Nothing about what follows changes that. The object your hand is resting on is made of atoms. This is not news, but the atoms are made of nuclei surrounded by electrons, and the electrons are quantum mechanical objects, no definite position until measured, no definite momentum, carrying probability distributions through space rather than fixed trajectories, governed by wave functions that spread and interfere and collapse only when something interacts with them. These electrons are not classical. They have never been classical. The quantum behavior is not something they grow out of at larger scales. It is what they are, at every scale, in every object, in every surface you have ever touched. The solidity comes from this, not between it. The reason your hand does not pass through the blanket is, at the deepest level, a quantum mechanical reason. The electrons in the atoms of your hand and the electrons in the atoms of the material repel each other. Electromagnetic repulsion, familiar from classical physics. But the reason those electrons are arranged the way they are, occupying the spatial distributions they occupy around their nuclei, distributed across energy levels in the specific pattern that determines chemistry and bonding, and ultimately the macroscopic properties of materials. That reason is quantum mechanical. The Pauli exclusion principle, which states that no two fermions can occupy the same quantum state simultaneously, forces electrons into a hierarchy of energy levels rather than collapsing them all into the lowest available state. Without this principle, atoms would not have the structure they have. Without that structure, chemistry does not work. Without chemistry, the material your hand is resting on does not exist in any form that has the property of being solid. The pressure you feel is the Pauli exclusion principle, expressed at human scale. Feel the warmth where your hand meets the surface. Heat at the atomic level is motion, the thermal vibration of atoms around their equilibrium positions, the kinetic energy distributed across a material according to the statistical laws that govern large numbers of particles in contact with a thermal environment. The temperature of the blanket or pillow or mattress is a macroscopic description of something happening at the scale of atoms and electrons. Constant, irregular, distributed motion, each particle vibrating with an energy that fluctuates from moment to moment, the average of all those fluctuations producing the temperature that your skin registers as a number on an intuitive scale from cold to hot. The equilibrium positions around which the atoms vibrate are determined by quantum mechanics. The bonds between atoms, the forces that hold a solid together and give it the shape it has, arise from the behavior of electrons shared between atoms, electrons whose probability distributions spread across multiple nuclei, and lower the total energy of the system in a way that classical physics cannot account for. The solid is held together by quantum mechanical bonding. The warmth is the classical statistical description of quantum mechanical vibration. You're feeling quantum mechanics. You've always been feeling it. The classical appearance is real, and the quantum substrate is real, and they are not in tension. They are the same thing described at different levels of resolution. The lamp, if there is one, emits light. The emission is quantum mechanical. An electron in an atom absorbs energy and jumps to a higher energy level, a discrete level, not a continuous range, because the quantum mechanical structure of the atom only permits certain energies and not others. Then the electron falls back, emitting a photon whose energy corresponds exactly to the energy difference between the two levels. The color of the light is determined by this energy difference. The discreteness of atomic energy levels, which is entirely a quantum mechanical phenomenon, is what produces the specific colors that different materials emit when heated or excited, the yellow of sodium, the red of neon, the pale blue of argon. The light in the room, if there is any, is a quantum mechanical phenomenon made visible at human scale. The ceiling, if visible, reflects that light. The reflection is classical in its gross behavior. The angle of incidence equals the angle of reflection. The surface scatters light in a distribution determined by its roughness. But the absorption and re-emission at the atomic level that underlies the reflection is quantum mechanical. And the ceiling itself, its paint, its plaster, its structural materials, is held together by quantum mechanical bonding, maintained in its solid form by the Pauli exclusion principle preventing its constituent electrons from occupying the same states, thermally vibrating at a temperature determined by the quantum mechanical nature of the bonds. There is a realization that forms slowly here, not arriving all at once, but building across the description, the hand, the warmth, the light, the ceiling, that the quantum world is not elsewhere. It is not in the laboratory, not in the particle accelerator, not in the dilution refrigerator maintaining a superconducting qubit at millikelvin temperatures. It is in the blanket, in the temperature of the air in the room, in the pressure of a pillow against a cheek. The everyday world is not the place where quantum mechanics stops applying. It is the place where quantum mechanics has already finished its work, where the consequences of superposition and exclusion and quantization have compounded into stable classical-looking structures that are navigable at human scale without any knowledge of what produced them. This seems like an important distinction between quantum mechanics as something that happens elsewhere, in special conditions to special systems, and quantum mechanics as the underlying process that produced everything, still running, still operating, its signatures averaged out into the textures and temperatures and resistances of the ordinary world. The first picture is simpler. The second is accurate. The object your hand was resting on is still there, still solid. The atoms in it are still vibrating, the electrons are still occupying their quantum mechanical energy levels, still obeying the exclusion principle, still holding the bonds that give the material its macroscopic properties. None of this required your attention, none of it required any attention at all. The quantum mechanics has been operating in the material for longer than this building has existed. Longer than the species that built it has existed, producing the same classical appearance through the same underlying process, indifferent to whether anyone nearby understands what is producing it. The solidity is a result, not a given. The warmth is a result. The specific texture of the surface, the way it gives slightly under pressure or holds firm, the colour it would appear in daylight, all of it downstream from quantum mechanical processes that have no classical explanation, operating at scales where no human hand has ever directly reached, producing at the surface a world that feels thoroughly reassuringly classical, which it is, and which it isn't, quite, depending on the resolution at which it is examined, and how far down the question is willing to go before it rests. The hand rests, the surface holds. Beneath both, without pause, the quantum substrate continues. There was a time, not long ago in the history of physics, when asking what a particle was doing before it was measured felt like a reasonable scientific question, the kind of question that more careful experimentation or more sophisticated theory would eventually answer. The kind of gap in knowledge that patience and ingenuity would close in the way that gaps in knowledge had always been closed, by looking more carefully, thinking more precisely, building better instruments that could reach further into the detail of the world and return with facts that cruder tools had left obscured. That expectation did not survive contact with the evidence. What happens before the question is asked is not, it turns out, simply the answer, waiting in a hidden location. The pre-measurement state of a quantum system is not a state of concealment. It is a state of genuine openness. The superposition that the wavefunction describes is not a veil over a fixed fact, but the actual physical condition of the system, the most complete description available. Complete not because we have gathered all the relevant data, but because there is no further data to gather. The hidden variable approaches that tried to restore a pre-existing fact beneath the quantum formalism were tested through Bell's theorem and the experiments it inspired, and they failed. The failure was not approximate. The correlations between entangled particles exceed the limits that any hidden variable theory consistent with locality can produce, and the excess is large enough, and the experiments are careful enough that the conclusion is not seriously contested. Before the measurement, there was no fact about the outcome, not a hidden fact, not an inaccessible fact, no fact. This consequence lingers in a way that other quantum results do not, partly because it touches something that feels foundational rather than merely counterintuitive, something about the relationship between time and reality that goes deeper than wave-particle duality, or the uncertainty principle, or even entanglement, which are strange in ways the mind can eventually accommodate. Building new intuitions through familiarity with the formalism and the experimental results, developing something like comfort with the strangeness, even if not quite understanding it in any way that connects to ordinary experience. The absence of a pre-existing fact is harder to accommodate. It is not strange in the way that superposition is strange, the way that a particle going through both slits is strange but containable, strange in a way that the mathematics handles cleanly and the experiments confirm without ambiguity. It is strange in a way that reaches backward through time, that changes what can be said not just about the present state of a system, but about its past, about the question of what was happening before anyone asked. Quantum mechanics has a specific way of handling the past that differs from classical mechanics in a subtle and important respect. In classical mechanics, the past is fully determined by the present state. Given the current position and momentum of every particle in a system, classical mechanics can in principle be run backward, and the history of the system can be reconstructed with arbitrary precision. The past is recoverable, at least in principle. It was always there, fixed, waiting to be traced. In quantum mechanics, the situation is more complicated. The wave function evolves deterministically backward in time under the Schrödinger equation, just as it does forward. The equation is time-symmetric, treating past and future with equal mathematical standing. But the measurement outcomes that punctuate the wave function's evolution are not recoverable in the same way. When a measurement is made and an outcome is obtained, the wave function collapses, or in many worlds branches, and the other possible outcomes are no longer accessible from within the branch where the measurement was performed. The history of which outcomes actually occurred cannot be reconstructed from the current wave function alone, because the wave function, after measurement, reflects the outcome that was obtained rather than the full superposition that preceded it. The past, in this sense, is partially constructed by the measurement rather than simply recorded by it. There is a hesitation in stating this too confidently, because the language of construction implies something stronger than the physics necessarily supports, and the line between saying the measurement selects an outcome from a pre-existing set of possibilities and saying the measurement brings the outcome into existence is a line that the formalism does not clearly locate, leaving the interpretation to do work that the mathematics, strictly speaking, does not assign to it. What the physics does say clearly is that asking what the particle was doing before the measurement is not like asking where a classical object was before someone looked at it. The classical object was somewhere. The quantum particle was in a superposition, and the superposition is not a description of ignorance, but a description of the actual physical state, which contained no fact about where the particle would be found, only a distribution of probabilities for where it might be found, probabilities that were real, in the sense that they correctly predicted the statistics of outcomes across many repeated measurements, but not real in the sense that they pointed to a pre-existing definite value waiting beneath them. The question asked before the measurement, what is the particle doing right now, turns out to be a question of a peculiar kind, one that the physics suggests should be held carefully, rather than answered confidently, because the grammar of the question assumes a kind of definiteness that the physical state does not contain, and answering it as though the definiteness were there would be importing a classical assumption into a domain where the evidence has repeatedly shown that classical assumptions fail. This is tested here and allowed to remain uncertain. The idea that the question itself might be the problem that the absence of a pre-existing fact is not a gap in knowledge, but a signal that the category of question being asked does not fit the structure of the reality being questioned. That quantum mechanics is not withholding an answer, but indicating, through the structure of its formalism and the results of its experiments, that the question as posed does not have a referent in the physical world it describes. Whether this should be taken as a limitation of quantum mechanics, a sign that a deeper theory awaits, one in which pre-existing facts are restored and the question recovers its referent, or as a genuine feature of reality that any future theory will have to preserve, is a question that the current evidence does not settle, and that physicists with equal command of the formalism answer differently depending on commitments that lie, in the end, outside the formalism itself. There is something almost restful about leaving it there, in the way that certain unresolved questions are more comfortable resting places than forced conclusions. The question of what was happening before the measurement joining a small collection of questions that physics has not answered, because physics has shown with some care that the answer may not be the kind of thing that exists. The particle was in superposition. The superposition contained no fact about the outcome. The measurement produced one. What was happening in the space between those two moments, in the time after preparation and before detection, in the interval when the question had not yet been asked, remains in the most precise available description, genuinely open, not as a gap to be filled, but as the actual condition of the system, carried forward through time by an equation that required no answer until the world provided one. Before the question, there was the wave function, spreading, evolving, touching every possible outcome with some amplitude, none of them yet actual, all of them present in the only sense the mathematics provides, which turned out to be the only sense the universe required, right up until the moment when something asked, and one of them became the answer, and the others became the past that might have been. The question that opened this was simple in its grammar. Can something exist and not exist at the same time? No question mark was needed because the question was not really asking, it was pointing at something the physics had already answered, carefully, over the course of a century, through experiments conducted in basements and clean rooms and particle accelerators and optical laboratories, by people who did not agree on what the results meant but agreed completely on what the results were. The answer was yes, not yes in a loose sense, not yes as a metaphor for ambiguity or a poetic gesture toward mystery. Yes in the sense that the mathematical formalism developed to describe the behavior of quantum systems requires the simultaneous presence of multiple states before measurement, and that this requirement is not a theoretical convenience but a physical necessity. Remove it. Assume instead that particles always have definite states that measurements merely reveal, and the predictions fail. The Bell experiments confirmed this. The interference patterns confirmed this. The precise agreement between quantum mechanical predictions and experimental outcomes, sustained across decades and refined to extraordinary precision, confirmed this. Something can exist and not exist at the same time. The electron in superposition is spin up and spin down simultaneously, not in sequence, not in alternation, not hiding one value behind the appearance of two, genuinely both, in the only sense that physical evidence can establish genuineness. What the century of work did not settle is what this means. The answer to the original question arrived clearly. The interpretation of the answer did not. Copenhagen says the superposition is a description of what can be known, and the question of what lies beneath it is not well formed. Many World says both outcomes occur in separate branches, and the universe is the totality of all of them. Pilot Wave says the particle has a definite position guided by a real wave, and the superposition is a property of the wave rather than the particle. Cubism says the wave function, is an agent's belief structure, and asking what it describes independently of any agent is asking for a view from nowhere that no physical theory can provide. None of these is wrong in the sense of making incorrect predictions. None of these is confirmed in the sense of being empirically distinguishable from the others. They are different answers to a question that sits just outside the boundary of what the experiments can currently reach. This is not a failure of physics. It seems important to say that plainly, because it can feel like one. The most successful quantitative theory in the history of science, and at its centre, an unresolved disagreement about what it is describing. But the disagreement is not about the physics. It is about the ontology, about what kind of thing the wave function is, what kind of reality the quantum state refers to, what it means for a measurement to produce a definite outcome from an indefinite state. These are questions that the theory raises without answering, and that may require something beyond the current theory to resolve, or may not, depending on whether the resolution is empirical or conceptual, whether it requires a new experiment or a new way of asking. There is a private hesitation here before anything like a conclusion forms, because concluding feels like the wrong gesture for a subject that has resisted conclusion so thoroughly and for so long. And because the most honest thing that can be said at the end of this is probably not a summary but an acknowledgement, that the question is still open, that the openness is not a temporary condition awaiting resolution, but a genuine feature of the current state of knowledge, and that this is, in its way, one of the more interesting places that a question has ever arrived. The world did not simplify when quantum mechanics was confirmed, it expanded. The kinds of real multiplied. A particle in superposition is real. The probabilities it carries are real. The interference it produces is real. The definite outcome that measurement produces is real. These are not competing realities. They are successive descriptions of the same system at different stages of its interaction with the world, and all of them are accurate, and none of them alone is complete. What exists before it is measured exists in a way that the word exist was not designed to hold. The language was built for chairs and stones and people, for things that are somewhere specific and remain there while no one is looking, for a world of persistent, definite objects moving along continuous paths through time. What exists before it is measured exists in a way that the word exist was not designed to hold. The language was built for chairs and stones and people, for things that are somewhere specific and remain there while no one is looking, for a world of persistent, definite objects moving along continuous paths through time. Quantum mechanics found a world beneath that one, and the world beneath it does not behave the way the surface world behaves, and the language has been stretching ever since, finding new shapes for what it needs to describe, not quite reaching the thing it is pointing at, but getting closer with each generation of experiment and theory and careful thought. Something can exist and not exist at the same time. The physics says so. The experiments confirm it. The interpretation remains, honestly and perhaps permanently, a matter of genuine inquiry, not ignorance, not laziness, but the condition of a field that has answered its central empirical question and found that the answer opens into something larger than the question contained. The electron does not know it is strange. The wave function evolves without any awareness of the debates about its nature. The superposition holds in the laboratory and in the intergalactic void and in the atoms of every object in this room, and the world above it continues in its classical appearance, solid and warm and navigable, built from quantum foundations that have never required anyone to understand them in order to function. It is enough for now to know that the foundations are there, that the strangeness is real, that the question was worth asking and the answer, incomplete as it remains, is one of the genuinely remarkable things that careful attention to the physical world has ever produced. Sleep, if it comes, will come the same way it always does. Gradually, then completely, the boundary between waking and not waking crossed without any clear moment of crossing, which is, in its own quiet way, another kind of superposition, another held between, another state that resolves without anyone deciding when. The question stays open, so does the night. If this found you at the right moment, if the quiet and the physics settled something in you tonight, the channel page is there when you want more. Each video is made to be listened to slowly in the dark without needing to follow every word. You can find it by searching The Sleepy Physicist, and if you feel moved to leave a comment or share it with someone who might need this kind of rest, that is always welcome. Thank you for being here, and for staying all the way to the end of something that never quite finished, which is perhaps exactly how it should be.